Okay, guys. Hello, everybody. Good morning. It's a pleasure today to have as a speaker and introduce Joakim Rosdahl. He's an expert of hydrodynamic simulation. So he got his PhD in Lyon, where he is working now. And after some postdoc in Leiden, he came back to Lyon for a permanent position at the CNRS. So he's the author of a very important upgrade of the Ramses hydro code, an upgrade that includes radiative transfer. And today, so in general, he's an expert of hydro simulations and galaxy formation. Today, he's going to tell us something interesting about his last project that are the SPHINX simulations.
Thank you, Francesco, for the nice introduction and for inviting me to come here and speak to a large audience. So indeed, I'm going to talk about reionization. It's a project I've been working on for several years now, the SPHINX simulations, with these nice and very important collaborators in Lyon, in Oxford, Chicago, Yonsei, and Paris. If we look back further out in the universe, we also look further back in time, and eventually we see the cosmic microwave background, which exists just a few 100,000 years after the Big Bang. There is a wealth of important information from the CMB. The universe was very nearly homogeneous at that time. We can tell that the matter component of the universe from the CMB is about 5/6 dark matter, and only a small fraction is in the form of baryons. From theory, largely, and from observations, we know that this dark matter component it collapsed into a cosmological web of sheets and filaments and halos. The gas followed suit, fell into these dark matter halos, and started to form galaxies. These first stars and the first galaxies then emitted ionizing radiation, and some of that ionizing radiation seems to have escaped from those galaxies and started to reionize the intergalactic medium. So we have this scenario of growing bubbles of ionized gas that eventually merge, and the universe as a whole becomes reionized, so ionized again. There is a lot of unknowns about reionization. It's a very exciting field to work in because there are a lot of questions that we need to answer. We need to understand how radiation could escape from those galaxies. Did it actually come from galaxies? And if so, which galaxies did it come from? Did it come from the massive ones or the low mass ones? How can we observe galaxies that are in the process of reionizing the universe? How did reionization affect the growth of galaxies, especially dwarf galaxies? There are all kinds of questions that we need to answer. And it's also very exciting because reionization, the epoch of reionization, is sort of at the frontier in observational astrophysics. So it's the science case of, arguably, the science case of the JWST. There is also the SKA, which is coming up to basically observe reionization in progress. What are the sources of reionization? So most people think that it's galaxies that are responsible for reionizing the universe. So there is this well-known toy model that we can make for reionization, where we can describe reionization very simply as a competition. So this is the evolution of the ionized fraction of the intergalactic medium, and we can describe that evolution as basically a competition between the emission of ionizing radiation into the IGM, which is ionizing the gas, and recombinations of that gas. So then if we know these factors, we can integrate that equation and we can construct a reionization history of the universe. The main factor that goes into that equation is just the emissivity of ionizing radiation getting into the intergalactic medium. And dot ion, that depends on three factors in turn. So one factor is star formation rate density in the early universe, basically the number of stars forming per volume as a function of redshift or time. Then there is a conversion factor between that star formation rate density and the amount of ionizing radiation that a unit of stellar mass emits into its environment. And then there's a fraction of that radiation which can escape away from the interstellar medium of its galaxy into the intergalactic medium and contribute to reionizing the universe. This factor is increasingly unknown. The Stockmason rate density of the universe in the early universe, it's getting better and better known. From stellar population models, we roughly there is a factor of maybe 2 uncertainty here, but we roughly know this conversion factor. This we don't know at all. We really don't know the escape fraction from galaxies. If we focus first on this Stockmason rate density, we can take a luminosity function at high redshifts. And if we know that, we can integrate the luminosity function and we can get an emissivity, well, not an emissivity, we can get a Stockmason rate per volume at a given redshift, here at redshift 6. So then we can do that at many redshifts, and then we can construct a Stockmason rate density as a function of time or redshift in the universe. You can see already from here that there's a lot of error in this estimation. And largely this is because we are limited in our sensitivity for the luminosity function. So this is traditionally what we had before the JWST, and this is probably how far we're going to reach with JWST and sort of upcoming estimates. So there's still a lot of uncertainty how much this unknown region is contributing to the Stockmason rate density in the early universe, and that gives still a big margin of error. Okay. And then if we focus on the escape fraction, well, we can sort of start to observe escape fractions from local galaxies, the local universe. And if we do so, we tend to find that they're tiny. The radiation seems to not really escape from galaxies in the local universe, ionizing radiation. If we try to observe at high redshift, it gets almost impossible because the ionizing radiation, it cannot reach us by definition because the surrounding medium is still neutral and absorbs all that ionizing radiation. So at high redshift, it's almost a free parameter in our models. And actually, people kind of try to reverse engineer the escape fraction by assuming a Stockmason rate density and the observational constraints of the reionization history of the universe. You can put those parameters into that equation, and then what remains is basically the escape fraction that goes into this. And then you can integrate that and to get or you can fit that in a way to get a constraints on how the escape fraction, the global escape fraction from galaxies, evolves as a function of redshift. And this has been done largely in UV background models that are used in simulations, for example. And they again vary a lot because, like I said, there are variations in the Stockmason rate density. There are other error factors, but all these models pretty much. I'm just showing 2 examples here. What they have in common is that you have to start with a high global escape of ionizing radiation from galaxies at high redshift, just because otherwise you cannot reionize the universe. And you have to end with low escape fractions because that seems to be what you observe in the local universe. And also because if you don't, you get a too intense UV background at low redshifts compared to what we observe. So this is very difficult to confirm, both with theory and observations. It's kind of a functional evolution of the escape fraction, and it's also very hard to explain why there should be an evolution like this of escape fractions of ionizing radiation from galaxies.
Joakim, sorry, is the black one consistent with the Madao and 2014?
The black one, that's from Fauchegui, yeah. That's kind of a more up-to-date UV background model. Yeah.
But the star formation rate density evolution.
They also assume a different Stockmason rate density evolution than the Madao.
Okay.
Which I guess is more up to date. And I forgot to say, please interrupt if you have questions.
So this is what I'm doing. Can I just ask you a question? I missed something. In the ingredient to define the reionization history, there must be also somewhere the spectrum of the ionizing sources, because it depends also on how many ultraviolet photons they emit, right?
Yeah, so that's basically this factor, this L
In
here.
the L
Then,
factor.
yeah, so that comes from stellar population people. We basically just ask them, given per stellar mass formed, how many ionizing photons do we get intrinsically from that stellar mass?
What is the IMF within?
Yeah, and that varies. It varies depending on the IMF.
And metallicity as well.
And metallicity, so it's a factor of maybe 2 or 3 uncertainty.
So it is also a source of.
And I actually come to that a bit later because we can plug in different SED models and that gives us a bit different luminosity as a function of time for the stellar population. So it is one of the uncertainties, but it's probably the smallest uncertainty, even though it's like factor 2.
Sorry.
Yeah.
If I understand correctly, so it's reassuring that the quantity on the right, which is obtained through, you said, reverse engineering, it's still a fraction. It could have been 42 or 100. You still get something smaller than 1, meaning, okay, you're trying to fix the exact parameter, but it's reassuring that you need less than 100% of the.
That's a good question, and I don't really know. I mean, I guess there's nothing in the model itself that prevents you from having something higher than 1, but I'm sure they adjust that.
Yeah, exactly. But this is what you need to get the right reionization starting from the star formation model. So automatically you get something smaller than 1.
Yeah.
It's not by construction, so it's.
Yeah, so I'm not really sure
Okay.
what happens here. So yeah. Okay. So like there are many questions about reionization, but I'm sort of in this talk I'm going to focus on these 2. So what is the contribution of this fate end of the luminosity function to reionization? How much these galaxies contribute to reionization? And can we somehow find such an evolution in escape fractions and try to explain it with simulations? So to study this, you have to consider a huge range of scales. You have to consider, gas. You have to consider the cosmic web forming on cosmological scales, megaparsecs. Gas falling into these dark matter halos, forming galaxies, collapsing into molecular clouds where stars are formed. Then these stars inject radiation, supernova feedback into its surrounding medium, which cascades back to intergalactic scales where it could affect gas, prevent it from falling into these same galaxies. So it's a huge feedback loop. It's nonlinear, multi-scale, multi-physics, and multi-dimensional. And we need to run radiation hydrodynamical simulations to be able to try to understand what's going on. So that's where we come in with the SPHINX simulations. So there is a large amount of reionization simulations sort of on the market. Most of them, they traditionally go for large sizes of volumes. So what you really would like to do is to approach this cosmological homogeneity scales, which is like a 300 megaparsecs or more in width. But if you want to do that, you have to make huge sacrifices in your resolution. So typically, the larger the box, the smaller your spatial scales that you can resolve. So we kind of go on the opposite end with the SPHINX simulation. So we do make the sacrifice of having small volume in order to have high resolution. So we have the largest SPHINX simulation is about 20 co-moving megaparsecs in width. But we can then have pretty good resolution, so we can resolve the ISM of galaxies, a multi-phase ISM of galaxies with about 10 parsec size of cells, of gas cells. This plot is not completely up to date, so I made this plot a few years ago. There have been some additions to that recently. But I think we are sort of still the only simulations that can resolve tens of thousands of galaxies with a multi-phase interstellar medium, and try to sort of start to predict what are the escape fractions from these individual galaxies. So we use the Ramses code. Ramses is It's a public code that I actually worked a lot on during my PhD, like Francesco was mentioning, to add the radiation hydrodynamics to the code. So we run cosmological simulations. We include dark matter, of course. We have gas, which collapses into these dark matter halos and forms galaxies. This gas, when it becomes dense enough and under certain conditions, it forms stars. These stars then inject supernova feedback into their medium and heats creates these millions of kelvins warm galactic winds that flow out from the galaxies. The stars also inject ionizing radiation, which then some of it can escape into the CGM, certain galactic medium, and intergalactic medium. And we then track the ionization state of the gas, so we can track the evolution of the ionized gas everywhere in our simulations. So if you, these are just the main kind of ingredients of the SPHINX simulations. You can go to the SPHINX website, or you can look at the papers to find more details. Our largest box, like I said, is 20 co-moving megaparsecs. We have a highest resolution of 10 parsecs in the ISM of galaxies. When you get, Ramses is an adaptive mesh refinement code, so when you get away from the ISM of galaxies, the resolution becomes less and less. Cells become bigger. We can sort of resolve halos down to what we think is the atomic cooling limit, which is the limit at which halos can form stars. We have non-equilibrium cooling for hydrogen and helium. We have this recipe for bursty star formation, where the star formation can become very efficient locally under certain conditions, where the virial parameter, well, it depends on the virial parameter and the turbulence of the gas. We model supernova explosions with mechanical feedback recipe, which is an injection of momentum into the surrounding gas. And here, this is quite important. In order to suppress star formation enough in our simulations to kind of fit with observations at high redshift, we have to have a fourfold boost of supernova rates compared to what you expect from a Krupa IMF. Krupa IMF gives you 1 supernova explosion per 100 solar masses. And we basically had to calibrate our simulations to have 4 supernova explosions per 100 solar masses in order to get realistic observational properties of simulations. We include ionizing radiation, which we track on the fly. And in most simulations, we use the BPAS spectral energy distribution models, which is a public thing that you can download anyway. And this gives us a luminosity of the stellar population. So a stellar particle represents a stellar population, not an individual star. And this SED models gives us the luminosity per solar mass of the stellar population as a function of its age and metal state. Yeah, that's pretty much what I wanted to say about that. So here's just a movie showing the largest SPHINX simulation so far. So we call it SPHINX 20 because it's a 20 co-moving megaparsec volume. We see here the density, the gas density collapsing into this cosmological web. We see here ionizing radiation, which is being emitted from the stars forming in those galaxies. You can see the effect of the ionizing radiation on the temperature of the gas. So gas, which is blue, is neutral and very cold. Gas, which is white, is about 10 to the 4 Kelvin. This is photoionized gas. And gas, which is red, is galactic winds, so heated up by supernova. And then we can track slowly the reionization, so it's neutral gas fraction. And around redshift 6, actually around redshift 5 in the simulation, it becomes pretty much ionized. Okay. I forgot to time myself. So probably something like 20 minutes in. Right? Yeah. Okay, so here I just want to show a closer, a zoom in basically the same movie that I was showing before. So this is to kind of express what's kind of going on smaller scales in these simulations. So you'll see gas collapsing. Gas is kind of in these red colors here. And then you'll see radiation in a yellow color, if I remember correctly. So what's going on is that gas collapses into these galaxies. And when it becomes dense enough, it forms stellar populations. These stellar populations then, a few mega years later, they start to explode by supernova feedback. And when that happens, it creates channels for the radiation to escape from those galaxies. So you see these flashes of radiation. It's not like a light bulb that you turn on and it just stays on. You have flashes of radiation getting out into the IGM. And these flashes are really instigated by feedback. Okay. So that's what I want to show here. So this is actually not from SPHINX, but this is from a paper by Maxime Trepitch, who was also in Lyon. And this is with a kind of a precursor to the SPHINX simulation. So this is a cosmological zoom simulation following just one galaxy evolving as a function of redshift, and using pretty much all the same subgrid models that we use in SPHINX. So this plot shows three quantities. So first in red is escape fraction of radiation, of ionizing radiation from this galaxy. In blue is the star formation rate of that galaxy, and then in yellow you see the outflow rate. So this is galactic wind getting out of the galaxy. So the point to make here, as I was trying to make in the movie before, is that this escape of ionizing radiation from the galaxy is regulated by feedback, by supernova feedback. So you see that the escape fraction is very, very fluctuating. It has these occasional peaks. And if you look closely, these peaks, they always tend to follow a peak in the star formation rate, which is blue. So what's happening is the gas is kind of collapsing into the galaxy. You have no or little star formation rate, and then you get a peak in star formation. And then a few million years later, the most massive stars in the stellar population, they start to explode. And that kind of does two things. One, it creates a feedback episode, so you have a huge galactic outflows. And at the same time, you open up the galaxy for the radiation to escape from it. But at the same time, because you're dispersing the gas in that galaxy, you stop forming stars. So the star formation rate goes down again because of the feedback. And then soon after, the escape fraction goes down again because the gas is coming back and it's starting to absorb the ionizing radiation again. And this repeats again and again and again. It's called, it's referred to sometimes as breathing of galaxies, because they collapse, form stars, everything blows up, and then it repeats again and again. Okay, so now we can compare a bit the SPHINX simulations to observations. So keep in mind that this is something that we kind of calibrated our simulations. I told you we have this fourfold boost in supernova explosions compared to what you expect from reality. And this is what we had to do to kind of force this luminosity function. This is just a UV luminosity at 1500 angstrom. And it's just a count of galaxies at certain luminosities as a function of different redshifts in our simulations. And here in these muted colors, you see observational constraints at different redshifts. And the kind of dashed curve in each frame is the UV luminosity function in SPHINX without taking into account attenuation by dust in those galaxies. And then if you take that into account, we get these solid curves which tend to sort of fit the observations at all these redshifts that we have tested. So we go down here to redshift 5. And the same is also true for the Lyman alpha luminosity function. It's sort of that was actually not a calibration that we did, but it kind of comes automatically when we calibrate the UV luminosity function.
So the quantity, the main quantity here to which that observable is sensitive is the boosting factor of the supernova feedback.
Yeah, so if we don't do that boosting factor, then we completely overshoot. We have too many galaxies here at high magnitude to low magnitude. So bright galaxies, we have too many bright galaxies compared to what you see here in this situation.
Excuse me, and you compute the extinction, dust extinction, is it computed internally in the simulation? Or?
So that's done in post-processing. So we use basically assume, I don't remember even what factor, conversion factor between metallicity and dust.
Okay.
And then we just inject that into our post-processing. We use a Monte Carlo code to trace radiation, so UV radiation in this case, from the star and see how much of it gets out of the gas. Okay, and then we can look at reionization histories. So this is just the evolution of the volume-weighted neutral fraction of the IGM, of the intergalactic medium in the simulation as a function of redshift. So this is for a few versions of the SPHINX, just a few volumes of the SPHINX simulation. So this is the main simulation that I'm talking about, the largest one. And then we have variations. So these are old simulations that are just smaller volumes, so half the width. This is exactly the same as the SPHINX 21. And then in these two, we are just varying from this one, the SED model, the spectral energy distribution model. So in this case, it's just a bit earlier version of the BPAS model. And this is Bruzel and Charlot SED, which differs from BPAS mostly in the sense that they don't include binary stars in their stellar populations. So that gives you a bit different evolution of the luminosity as a function of time in the stellar population. And that gives you a completely different reionization history in the corresponding SPHINX simulation. So you only change the SED model, you get a very, very different reionization history. So there is a very sensitive dependence on that SED model that we assume. But it kind of, I mean, we completely fail without binary stars. We have to include binary stars in our SED. And then, depending a bit on the version of BPAS that we use, we can have a reionization history that kind of brackets the observation constraints that we have on reionization.
Sorry, I didn't understand. The change in the SED is reflected here in a big change in the fraction because of what? Of the spectrum of the radiation emitted by the stellar population, the mass function?
Hang on, just a bit.
Okay.
I'm coming to in the next slide after this. Just one more observational constraint that we can compare to, that's the Thomson optical depth, which is the optical depth to electrons, so it's to the ionized intergalactic medium. This shaded region is constrained from Planck, and all our simulations that do include binary stars, as long as they include binary stars, they kind of fit within the margins that are from Planck. So at least in terms of that, it's also simulation is okay. So then we come to the effect of these binary stars, SEDs. So to first order, it comes down to escape fractions. So now if we look at the evolution of, this is the global escape fraction in different SPHINX simulations as a function of time. This green line here is without binary, so this is Bruzel and Charlot. And the corresponding simulation with BPAS is well, let's look at the blue one, actually. That's the kind of earlier version of BPAS. And there's a huge difference in the escape fractions. So assuming binary stars enhances escape fractions from galaxies in our simulations. And now we have to figure out what's the reason for that. So here, if we integrate just take the spectra from each of those population models, we integrate them to get ionizing luminosities as a function of age of the stellar population. This is just for a low metallicity that I've selected here, which kind of corresponds roughly to the metallicities that we have in SPHINX. At early times, they are more or less the same luminosities. The luminosity at early times is very insensitive to whether or not they are binary stars. And that's just because the luminosity here is completely dominated by most massive stars. Then, when these massive stars start to explode, that starts around 3 million years into the stellar population, you start to get a strong dimming of the stellar population just because the most massive stars are exploding, they're disappearing. And then you start to see huge differences. And these differences are due to, there are these binary companions which are orbiting close to each other, and they start eating gas from each other. And when that happens, you have these exposed helium cores, which are very strong in ionizing radiation. And that leaves you to a pretty big difference at late times, at fairly high ages, between having binary stars and not having binary stars. Now, when you insert that into a simulation of galaxies forming, having feedback, starburst episodes, feedback, escape. In the beginning, you have gas flowing into those galaxies, and you have stars forming. There are young stars, but there's not yet any feedback. There are no supernovae yet. So the gas is there. It's absorbing all the copious quantities of ionizing radiation that are being emitted. So there's no escape. There are high luminosities, but none of that radiation can escape from the galaxy. So here you really don't care what luminosity is high, but none of it gets up. Okay? And then at this red line here, you start to have supernova explosions. So at this point, you start to disrupt the ISM of the galaxy, and you start to have radiation getting up the galaxy. So it matters here what's the luminosity of the stellar population. And because even if though the actual luminosity is much smaller than it was in the first few million years, it matters that it's much higher with binary stars than without binary stars. So even if there is just a fraction of the total radiation which is escaping at this advanced stages, it matters a lot whether it's a bit more or a bit less. Okay. So now for the remainder, we can stick with the GPAS model because it kind of works. It doesn't work without a binary star. And we can look at in the SPHINX simulation which galaxies are kind of dominating the reionization process, and how the Lyman continuum production and escape correlate galaxy properties. So first of all, we can look at galaxy mass. So this plot shows escape fraction in blue as a function of galaxy mass in SPHINX. So this is just stacked snapshots from very high redshift to the end of the simulation. And there's a very clear correlation in the sense that there is a peak in escape fraction, which is highest for these intermediate massive galaxies around 10 to the 7 solar masses. For high masses and for low masses, the escape fractions are tiny. For high masses, it's very easy to explain. It's just that when the galaxy becomes massive, the gravitational potential is large enough that supernova explosions, they are not disrupting significantly the ISM of the galaxy. So even if you have a starburst and supernova explosions, it's not really destroying the galaxy, and there's still plenty of gas around to absorb all the ionizing radiation. At lower masses, it's a bit harder to explain, but there is kind of a lack of correlation between supernova events. There are not these very strong starbursts that have huge explosions happening in those low mass galaxies, and therefore we tend to have low escape fractions. Also, the red curve here shows the cumulative intrinsic luminosity as a function of mass. So basically, you can see, for example, at 10 to the 7 solar masses, you can account for something like 35% of the total ionizing radiation emitted intrinsically. But then, because the escape fractions are fairly high for these intermediate mass galaxies, if you account the cumulative escaping ionizing luminosity, you get a much higher contribution from those galaxies around 10 to the 7 solar masses. And this mass range between 10 to the 6 and 10 to the 8 then accounts for less than 50% of the intrinsic ionizing radiation. But because they have high escape fractions, it accounts for much larger fraction of the total escaping radiation.
So is stacked at high?
Yeah.
Yeah. So these galaxies should have been involved in much less massive galaxies in terms of stellar mass at the present day. Do you have a map between these masses and present day masses?
No, and this simulation actually only goes to redshift 4.8.
Okay.
But at each snapshot that I'm considering, I'm just considering the mass of the galaxy in that given snapshot. So it's not really considering the present day mass or anything like that. It's just the mass at the time that we are measuring the escape.
Would it be possible to guess how much is the blue line going to change to the right part of the plot if we also include stuff like quasar feedback?
There are people that have done this, and even with SPHINX-like simulations, and they tend to find that there is a bit of a boost in escape fractions at the massive end due to AGN feedback, but it's only for rare galaxies. I mean, these galaxies, they have to be massive enough that they are very rare at these high redshifts. So even if they have somewhat high escape fractions, they don't contribute really to reionization. That's kind of what people tend to find. But it's still a bit of it's not a completely answered question. But just to be clear, we don't include AGN in these things. So we can compare that a bit to other simulations of escape functions from galaxies. So this is just what I was showing you. This is from fire simulations and at different resolutions. So this is just the same kind of plot. These are escape fractions as a function of mass. And with low resolution, they at least get a very similar form of the escape fraction, which tends to get lower with higher mass. The peak is about an order of magnitude higher than in SPHINX. And that's actually probably related to the strength of feedback. So in the fire simulation, feedback tends to be quite strong. There are very strong hints that it's more efficient at suppressing stop motion than it is in SPHINX. And because there is such a strong correlation between feedback and escape fractions, it's kind of natural that when you have stronger feedback, you tend to shift that peak to more massive galaxies. And a bit worryingly, if they increase their resolution, there remains a hint that there is this turnover, but the magnitude of the escape fraction it's completely unconstrained with resolution. It's not converging with resolution. And we do have a hint of the same thing happening in SPHINX. So what we can hope is that the form stays the same, but the magnitude is probably not converging with resolution. In other simulations, this is the cosmic dawn simulations. These are large volumes with much lower resolution. But amazingly, they find a very similar form for the escape fractions, which tends to go very low with halo mass. Renaissance simulations, another set of reionization simulations, they also have this evolution that massive galaxies have low escape fractions. And this is completely what you should expect if escape fractions are regulated by supernova peaks. Bit more simulations that we can compare to. This is from TNG. These are not RHD simulations, so that changes a bit your result, I think. They have a kind of a hint of the same evolution, but and they have AGN here at high masses. This is the Thiessen simulations, which are more or less based on the same subgrid models as TNG, but with RHD. And they have this weird functional form where the escape fraction becomes very high at high galaxy masses. They don't really explain why, so I'm not sure whether it's due to their AGN or not, but they do conclude, like I was saying, that even if escape fractions tend to be high here for them, these galaxies are just so rare that they don't really contribute to reionization. And then with SPHINX, we can use this correlation between escape fraction and galaxy mass to conclude what's the relative contribution of galaxies at different masses to reionization. So that's what these colored solid curves show. So for example, you can see here that galaxies in the mass range 10 to the 7 to 10 to the 8 solar masses, they contribute to something like 20%. 40% of the total ionizing radiation that gets into the AGM and reionizes the universe. The so-called oligarchs, these massive galaxies in the reionization community, they have sometimes been referred to as the oligarchs. They don't contribute much, even if you can see from the dotted line, they contribute quite a lot to the intrinsic ionizing radiation emitted, but because their escape fractions are so low, they contribute much less to the escaping ionizing radiation getting into the AGM. Okay, then we can look at this predicted whether we get this predicted evolution of escape fractions that seems to go from high at high redshift to low at low redshift. So we can look at the global escape fraction in SPHINX simulations. And indeed, what we tend to get is even though it's not as extreme as in these UV background models that people use, an example of which you can see here and here, we still do get an escape fraction that evolves from relatively high at high redshift to low at low redshift. And that's very exciting because it kind of roughly fits with what we get in these UV background models. And then we can try to explain, at least using SPHINX, what drives this kind of evolution in our systems. I'm starting to be out of time now. 5 minutes. So there have been a few papers. I mean, nobody has gotten this kind of evolution with simulation. So people have tried to explain why there should be such an evolution in these UV background models. And these have been mostly speculations, but there have been speculations about this evolution being driven by galaxies simply becoming more massive as a function of redshift. So you already saw that massive galaxies tend to have low escape fractions. So if you start to be more and more dominated by massive galaxies, you should naturally have an evolution towards lower total escape fractions. The same could be true for metal-rich galaxies. I didn't show you, but metal-rich galaxies also tend to have low escape fractions. And there is an evolution towards more metal-rich galaxies with lower redshifts. So we can try to look at that in SPHINX to see if these factors explain the evolution in the escape fraction. So here is the same plot as I was showing before, correlation between galaxy mass and escape fraction. But now I'm splitting into different redshifts from high to low. So, okay, the point here is that this curve, the peak stays in pretty much the same place from high to low redshift, but the magnitude of the peak is evolving quite dramatically with redshift. So now if you fix a galaxy mass, you take a 10 to the 7 solar masses, for example, where the peak is, you find that the escape fraction for this fixed galaxy mass, it goes down with redshift. So that means that the evolution in the escape fraction with redshift cannot be explained by an evolution towards more massive galaxies. Because if that was the sole reason, peak should be exactly the same at all redshifts. And then we can consider the same thing for metallicities. So these are metallicities of galaxies. Again, the escape fraction is low for high metallicities, and in that sense, there is no evolution with redshift, but the magnitude of that peak in escape fraction with metallicity, it does evolve from high to low with redshift. So again, you cannot really explain the evolution in the global escape fraction being from the evolution in metallicity of galaxies. Okay. Then the third speculation that we can consider is that that's been made by some people is that a lower kind of intensity or burstiness of star formation could lead to smaller escape fractions, a function of redshift. So if we look at just the evolution of the intensity of star formation in SPHINX, indeed we find that this does go down with redshift. So we just look at the specific star formation rate of galaxies, which is star formation rate divided by mass, and we just average that for all galaxies in SPHINX. We find that it doesn't really matter how we measure it, it always goes down with redshift. Even if we fix the galaxy mass, it still goes down with redshift. So then we can look at the correlation between escape fraction and basically specific star formation rate of galaxies. And we find three important details here. So first of all, there is a very strong correlation between specific star formation rate or burstiness of star formation and escape fractions. It's very strongly peaked for galaxies that have the highest specific star formation rates. Second, this correlation, it doesn't change really at all with redshift. It's more or less the same. It becomes less noisy, but it's more or less the same from high redshift to low redshift. And then you see what you actually already saw in the slide before from the red curve, that the total emissivity of galaxies is shifted from galaxies with very high specific star formation rates at high redshift to relatively low specific star formation rates at low redshifts. So if you take these three factors into account, what that leads to is just very naturally an escape fraction, a global escape fraction that decreases with redshift. This is just another way to show the same thing. So here we are isolating, we are splitting galaxies into different classes in specific star formation rates, and looking at the evolution of these individual classes of galaxies over redshift. So the solid curves here show the global escape fractions for these different classes. And indeed, they for each class, it's more or less the same. It's a bit noisy sometimes, just because there are not so many galaxies that have extremely high specific star formation rates at any given time. But the global escape fraction stays fairly constant over for a given specific star formation rate of a galaxy. And again, for individual galaxies, this is changing all the time. We are just taking in each snapshot, splitting the galaxies into these categories. And then in the dashed in the shaded regions, you see the contributions to the intrinsic ionizing luminosity for each classes of these galaxies. So you see that in the beginning, at very high redshift, the intrinsic ionizing luminosity is completely dominated by galaxies with extremely high specific star formation rates, with high escape fractions. And then as you evolve in time, it becomes increasingly dominated by galaxies that have low specific star formation rates and have low escape fractions. So if you just convolve these two functions, what that leads to is the red global escape fraction, which goes from relatively high to relatively low for all the galaxies.
Excuse me, but are the ages that they see, are they the ages of the galaxy population, or
The ages.
I mean the
No,
sorry.
This is just just redshift. It's just the
By the way,
age
towards
of the universe.
towards 0 means, by the way.
Ah,
Towards
0.
zero.
So I'm going to skip this part because super important. I just want to say a few things about the most recent thing we did with SPHINX, which is a SPHINX data release. So we have mock observed selection of SPHINX galaxies. We have taken all galaxies that have star formation rates larger than 0.3 solar masses per year, because we thought that this is kind of the limit at which JWST can observe galaxies at high redshift. And we have mock observed those galaxies with the Rosdahl Monte Carlo code, which traces, like I was explaining before, that traces radiation from the gas and stellar populations, and we create images and spectra that we have then put online. So you can access this. There was a paper that came out last year, and then that points to a website where you can download these SPHINX galaxies. And you have all these intrinsic properties of galaxies, star formation rates, even star formation histories, escape fractions, etc. And then you have mock images like these, and then you have spectra from star populations, from the gas, and you have both continuum emission and lines, selected lines from the gas in these galaxies. So here's just an example of one of the spectra from the data release. We also include the JWST filters, so you can basically mock observe these galaxies with JWST compared directly to JWST observations. And then we include, for example, star formation histories for these individual galaxies. So this galaxy corresponds to it's very hard to tell, but it's the kind of red curve here. And now the observers, they can download this and they can play the game of trying to feed this spectrum to their models and try to see if they derive the actual physical properties of the SPHINX galaxy using their models and even their star formation histories. And it's actually already proving quite useful for the community to improve their models and to interpret JWST observations. And that's where I leave. I'll just leave that here, and then you can ask questions.
So very small announcement while you think about questions. After this round of questions, there will be a short meeting with the students and with the young people if they want, if they are interested, of course. Okay. Now
So there is some question here from home.
Yeah.
The defect, is it included also this the question of like stellar stars? How can it eventually contribute to the preheating of the gas before the supernova?
Well, so we include the radiation feedback. So that's something that kind of is automatically included because we have this ionizing radiation. We don't include the stellar winds. And I'm collaborating with people who have been trying to inject stellar wind into much smaller scales with molecular power. And you find that the only thing it does is make your simulation smooth. But I would guess probably it doesn't have a big effect. I think some effect it's ionizing radiation. That said, even that is probably underestimated a bit here because we simply lack the resolution. So if you increase the resolution, you can get larger from that show you feedback and radiation.
More questions? Yes, Fabio.
I was wondering, so since the escape fraction is driven by the evolution of specific stuff from which rate, what is driving the evolution of specific stuff from which rate? Is that you don't have enough cold gas because
There's always, you answer one question and you always have another question. I don't really know, but I think it's just the fact that the universe is expanding. It's more dense at high rate. There is more gas coming in more curiously, denser. There are more mergers. Single mergers kind of tend to trigger these events as well.
is it also the heating of the gas entering? So if you have hot gas versus cold gas, it kind of impact the transformation.
I'm not too sure about that. I think it's more just I think it's more just the amount of gas. But it's a bit it's something that I would like to look at more, especially try to figure out whether mergers.
Livia.
Yes, I have a very naive question regarding the fitting of the UV luminosity functions. So, like you were showing that SPHINX is behaving very well in fitting like the data up to, I don't know, before GWC, I would say. So, are you using or planning to use the new GWC data to maybe see if anything like new points, even at higher redshift that now we have? Like, and if this is the case, is telling you something regarding the processes that and the escape fraction and the dust probably attenuation or things like that in the SPHINX simulation? Yeah. Because the plot that you showed was, I think, pre-GWC.
Yeah, absolutely. So things are changing fast, right?
Exactly.
And they're changing so fast that I mean, they're evolving a bit. Some of these observations tend to be not confirmed, right?
No, yeah.
But definitely, I think there is an emerging situation where there are possibly more massive galaxies than we thought before, and so SPHINX and probably every other simulation is going to have a problem explaining.
Okay. No, just
we need to react to this. Many are. I think many people are trying to run new simulations to figure out what's going on.
They are changing faster than the time required to complete
run
the simulations.
Try for computing time and the work is not.
Let's go back to the plot where you show the ionization fraction as a function of redshift. So while you try to find it, I try to make it. So I come from a completely different background. I study kinematics oriented Dovich effect from the large scale structure. This when I see these plots here, so like the duration of reionization according to this model should last for an interval of redshift of say 5, 6 or so. So I imagine that with these models there are these big bubbles during this very long time that stay there. In principle, these bubbles should imprint a signal in the CMB with the kinematics method of this effect that around the multicolor of the L3000. However, observations, they don't seem to see this, at least because there are several works now by SPT, some of Politecnico, that they have put, according to me, quite stringent upper limits. I never see this mentioned when
So the prediction is that it should last a very short time.
either very short time or it should be somehow very uniform. I mean, it's not a strong constraint, but I think that those results should at least be mentioned as observational constraints. Are you aware of it?
Not really. No.
Not, so we can maybe talk about it a little bit.
Totally point me to the literature. And maybe to add to that, I think when SKA comes online, there should be a lot more constraints on the growth of these bubbles as much as controversial. But that's maybe potentially
More questions? Yes.
Thank you for the nice talk. Can you say a little bit more maybe on the IMF calibration for the supernova explosions? Is it only an amplitude-like calibration? So you offset the.
Yeah, so it's not even really an IMF. It's just, well, so integrating an IMF gives you the number of supernovae per solar mass. So you take a Krupa IMF, for example, that gives you almost one supernovae per 100 solar masses. So we've just taken that number and multiplied it by a factor of 4. That's all. Just because, so I ran a bunch of smaller volume SPHINX simulations and looked at the luminosity function that comes up, and just played with that factor, and found that you need at least a factor of 4 to suppress the luminosity function.
So the shape of the IMF or the luminosity function.
So that doesn't really come in. I mean, there's not really any other assumption that we make about the IMF. So it's, yeah, we're not really integrating any IMF to do this. It's much more kind of basic.
This supernova fraction can be somehow related with the observed supernova rays.
I'm not sure about that. Like observed in the local universe, or
yeah.
I think what you tend to observe, like in the Milky Way, is 1, maybe 2 supernova explosions per 100 solar masses. Factor 4 is you don't see that, definitely.
Okay.
There are some speculations that the IMF might be different at high redshift. But you know, I don't want to. This is just calibration. There are plenty of factors that could explain the tension. There are numerical problems. There is numerical overcooling, which is well known and happens in whatever code that you use. And there could be physics that are missing as well. Cost of radiation, for example. And resolution.
Sure. In any case, I think that now there is broad consensus about first population of stars having a compact IMF. So
okay, so that would help.
An higher supernova ray.
Last question, very quick one, please.
Yeah, but about the fact of the IMF. How does this connect with the SED?
You
should assume.
Yeah, not at all. So there is no, and there, I mean, it's completely discrepant, right?
Okay.
We're always assuming in a given simulation, we just feed in normally BPAS, and we don't change that at all. So that's another factor that we could vary, but you have to stop yourselves.
Yeah. Yeah.
Okay, thanks a lot to the speaker and to the audience.